Hi, everybody. This is Michael, and this is another meeting of the special interest group for Windows in the Kubernetes platform. Today, we don't have any updates from a SIG perspective, but Jason Messer from Microsoft is going to give us an update on native networking improvements, specifically how they affect Kubernetes, and give us a presentation with what's coming up next for Microsoft. So Jason, go ahead.
Okay, thanks, Michael. Thanks, everybody, for joining. Good morning or good afternoon, depending on where you're at. Yeah, I just wanted to kind of provide an opportunity or give you an opportunity to learn more about how we do networking in the Windows environment, and specifically how it relates to Kubernetes and some of the containers initiatives that we're driving right now. So I'm a program manager, as Michael may have mentioned, on the Windows core networking team. I can't see all the participants on the call, but I'm also being supported quite heavily by not only the SIG, but also by people in Microsoft itself, like Anthony Howe, Dinesh, Madan and his team, who have done a lot of the engineering work for us. And so we've really come together across Microsoft, across Azure, across Windows, across even the open source community to develop some native networking solutions for Kubernetes on Windows. So I just kind of wanted to give you some roadmap items, some vision that we have, and also kind of ask you to help participate in this effort, or at least it's actually us wanting to participate more with you guys, since I know you've been active already. So a little bit of motivation. I don't think I need much of this, since this is the special interest group for Windows, but there is a reason we should care about this, I think, and it's the number of Windows container instances is actually dramatically on the rise. We're seeing a lot of positive growth, and so there's a very quick adoption just since we've released this last fall, in fact, with the Windows Server 2016 release. A lot of customer interest, a lot of proofs of concept going on. A lot of people are doing either a lift and shift of their workloads from a Windows VM to now a Windows container, or maybe redesigning a lot of their applications to be more microservice based. There is a significant amount of excitement there with the Windows community. We're excited too to join in that, and also we want to support more of these mixed mode type clusters where we're doing Windows and Linux together. So a lot of the feedback we've heard from customers who we've talked to, they don't just want to run a Windows cluster or just a Linux cluster. They actually want to run both. Maybe services are doing Windows on the front end and maybe something Linux based on the back end. Is that something that the SIG has seen as well, that there's a desire to do kind of those mixed mode clusters?
Absolutely. There's kind of the two types of customers we've been talking to. One has been the guys that have traditional .NET workloads and they want to migrate them into the cloud. And when I say migrate is, containerize them and start taking advantage of a cluster manager like Kubernetes to orchestrate their workloads, because they see that there's a significant time saver and it's a significantly better platform for their use. And then there's folks that basically say, hey, now there's a platform that allows me to pick the best of breed type of component for my application, so I can pick and choose some Linux components, some Windows components, and build my app. So I could use a Redis backend running on Linux, which is the best platform for it, and then use an ASP.NET workload on the front end or something else. So the fact that they're going down this approach affords them the ability to enable such workload definitions.
Awesome. Okay, very cool. Yeah, so we're really wanting to work to improve and also expand some of the capabilities that we're giving for networking to support really any deployment configuration or environment and all the different network topologies that we've seen out there, both for on-premise and kind of private and public cloud as well. So we're moving in that direction. It's really a journey that we want to join you guys and have you join us as well. I think we could do a better job being more active in the SIG, and I'm hoping we'll move in that direction. I know several people are already very active, especially on the Azure side. So I think you'll see more and more of the Windows networking team start to be more active there. So just kind of a glance of where we came from. The containers initiative really started with our Windows Server 2016 release and that development cycle, which took a number of years. And so if you look back just a year and a half ago, maybe a little bit more, it was still using a lot of PowerShell to do a lot of the container network management, to set up all the plumbing, all the policies. It was a very manual intensive effort. It was built with a lot of the VM-based PowerShell commandlets for creating VM switches and NATs and so on and so forth. And so since then, though, we've really, we began adding support in some of the technical previews that you might have seen access to before Server 2016 was released. We created a new servicing layer called the host networking service. That's kind of a pluggable servicing layer to interface not only with something like Docker and user mode, but then also down below in the OS itself to figure out all this plumbing and do it for you. Also worked to create a Docker libnetwork plugin for Windows and added support for a bunch of different multiple networking modes and drivers. Right before Server 2016 was released, we actually had a major push to kind of get some more developer tooling in place. We didn't have the best support for things like Compose or service discovery. And so we added some of those features at the very end of Server 2016 release milestone last fall. We're continuing to do that, realizing that it's not just, kind of IT admins that we've traditionally targeted in the past, but also developers who are wanting to use these new workflows with containers and the different tooling that's available out there. And so things like supporting, having a better NAT story on Windows to support multiple prefixes, multiple types of virtualization like, VMs and containers and emulators that all might need NAT network access. Just to make the developer experience better. And now we're getting to the point where we're actually extending this out to scale out these services, not just on a single development node or one small deployment node, but across multiple node clusters. And so you may have seen, new overlay network driver with swarm support for the Windows 10 creators update, which was just released, I think, this past week. And there'll be something for Server 2016 coming soon, so stay tuned for that. And then just new features. I think we're wanting to be in this mode where we're continually innovating and developing and releasing new things. And so towards the end of this talk, I'll give you some more opportunities for how you might join us on that journey. So let's go ahead and go a little bit deeper now on the technical side of things. Just to give you kind of a high-level overview of what our virtual network stack looks like, I have a picture on the right-hand side that represents just a Windows Hyper-V host, basically. So we have, obviously, we have our own Microsoft hypervisor, which is Hyper-V. And then we also have, from a networking perspective, we have our Hyper-V virtual switch. This Hyper-V virtual switch is able to provide layer 2 connectivity to, VMs or containers and different variants of containers as well. And it does this through creating these network endpoints. And so we have different names for these network endpoints. There's some sort of a virtual network adapter, either a host VNIC or a VM NIC. And so that basically provides that layer 2 connectivity to these VMs or containers through usage. As far as isolation is concerned, we actually have a bunch of different isolation mechanisms. To start, I'll start with the compute side of things. We have two different types of Microsoft containers, or two different types of Windows containers. One is the Windows Server containers, which shares the kernel with the container host itself. The other one is the Hyper-V containers, which actually has an isolated kernel and runs inside an optimized utility VM to provide that additional isolation. From a networking standpoint, then, we have this idea of a network compartment, which is very similar to a network namespace. So each time a container endpoint is created and attached to a container, it's placed within its own networking compartment. The host itself has a default compartment where all the host networking stack resides. So we have Hyper-V containers on the left of this picture connecting to a VM NIC, and then Windows Server containers on the right. So I want to talk a little bit about security after we've done isolation. Right now we've done a lot of work with the Windows firewall to basically enlighten it to be aware of containers and these networking compartment ideas. So Windows firewall behaves somewhat differently between Windows Server containers on the right and Hyper-V containers on the left. And so there's some default rules there that are created in the Windows firewall itself. And also, whenever a service is actually exposed, like doing a Docker run command and publishing a port, not only is a port mapping created, a static port mapping, but also then a Windows Firewall allow rule is plumbed in. Again, this was something that had to be done manually just a year or so ago. We're actually innovating quite a bit in this space, and so there'll be some more announcements and more opportunities for you to participate here, because we want to make this better. From a network management perspective, again, I talked about this host networking service that we added as a servicing layer between the user mode apps and the OS itself. And so it's really responsible for a few different things. And it works in conjunction with a host compute service. So we have host compute service that's kind of bringing up the VMs or the containers as the case may be, and the host networking service that's handling all the network plumbing behind the scenes. And so whenever Docker client or maybe an orchestrator invokes some commands on the Docker REST API, it's actually flowing through that Docker engine through our Windows libnetwork plugin and interfacing with the host networking service. That host networking service then is able to create a network. Network's usually represented by a vSwitch for each network. It will create any of the NAT and IP pools that are needed and manage those IP pools for some of the networking modes. It'll also work with the host compute service, HCS, to create the correct endpoints and put those endpoints in the correct network compartment, and then assign IP addresses, DNS, routing information to those endpoints in the container itself. And then lastly is the policy pieces, such as, as I mentioned before, if you have a port mapping, either a static or a dynamic port mapping, it'll go ahead and create those rules in WinNat. It will plumb the correct Windows Firewall rules as well. So this is really a big table I don't expect to go through right now, but we do have a bunch of different networking modes that are exposed through our Docker libnetwork plugin, including NAT, transparent, overlay, L2 bridge, and L2 tunnel. I'm going to just pictorially show what these modes look like, and then people can come back to the slides later for reference. So NAT, the way we implement NAT, this is similar to the bridge mode in Linux. Basically, we have a component today called WinNat that actually does that natting operation. It provides an internal prefix for the containers, and it also has, using host networking service, IP addresses are actually allocated and assigned from that subnet prefix pool to an individual container endpoint. For external access, it's really kind of it's a routing operation. We have what's called a management host VNIC that's sitting off to the side there, and it has the gateway IP address of that NAT network assigned to it. All the default routing gateways for all these containers then will go through that host VNIC and then can be routed out externally and back in internally for different port mappings that are created. So that's NAT. The next mode I want to talk about real quick is the transparent mode. This mode basically provides raw access from the containers to the physical network or the container host network underneath. And so we have to be careful with this mode since there's no address translation happening, there's no encapsulation going on, it's all just the raw frames, all the MAC addresses, all the IP addresses are visible on the physical network itself. For this mode, H&S kind of, I would say, gets out of the way. We can do static IP assignment if we specify a subnet, or we can do dynamic using an external DHCP server. Just a quick note, if the Hyper-V host or the container host itself is actually running as a VM, we need to make sure that we're doing MAC spoofing on that VM network adapter, because it's going to be seeing all the MAC addresses from each container running in that container host on the physical network. So that's a security concern, obviously, and something we don't really recommend. We've designed some other networking modes to overcome some of those limitations. Next one we're really excited about talking about is overlay. We announced support for overlay in the Windows 10 Creators Update, and if you had some of the Insider Program preview builds, you would have been exposed to this in the past. But basically, we have a new forwarding extension component called the Virtual Filtering Platform, VFP. It does this VXLAN encapsulation operation for us in the container host itself. So we've previously used this for our software-defined networking stack in Windows Server 2016, but that had a dependency on the network controller itself. What we've done now is basically remove that dependency, kept the same data plane, but we used the host networking service to program all the different policies and flow engine rules into the VFP extension itself. So we can create these overlay tunnels to separate different container networks from each other. So in this picture, basically we just have two networks, a .1 and a .2/24 network, and across two different hosts. This is all done through Docker Swarm mode today. Docker Swarm mode provides the KBS store and the Docker engine itself to send out what the different mappings are between the inner and outer IP addresses. L2 Bridge is a mode we're going to start recommending more, especially I think for Kubernetes-based deployments. It's similar to the transparent mode, except that it does a MAC rewrite on ingress and egress. And so we're using that virtual filtering platform, the VFP, to actually update either the source MAC or the destination MAC address on ingress and egress for that container traffic. So this saves on the number of MAC addresses. If this was plugged into, an actual physical network switch port, instead of having to learn all the different MAC addresses and overwhelming physical memory in those switches, basically it's just going to see the one MAC address from the host itself. And then the VFP extension is going to be the one that does the translation, that layer 2 address translation. The last one I want to talk about really quickly is the L2 tunnel mode. And this is really designed specifically for Azure. And so in this mode, we have the Windows container hosts, which are VMs. VMs themselves are connected to an Azure virtual network, in fact. And so we still have that tunnel, and I believe Azure uses NVG or eTunnel. Connect the virtual machines and containers to an Azure virtual network. The thing about this mode is that all network traffic from the container host is forwarded down to the physical host's VFP extension, where all the policy is applied for encapsulation, for network security groups, for quas, so on and so forth. So those are the 5 modes that we support today. And again, here's an overview, and I'll let you guys reference this later on when I make these slides available in the presentation. It talks about some IP address management, how we do that as well. We have different static and dynamic allocation and assignment schemes depending on the networking mode you're actually using. All right, so now I want to deep dive a little bit further into how we actually do Kubernetes networking in Azure Container Service itself. I know the group has been working a lot with cloud-based plugins, OVS and OVN controller, and I saw a great demo by Michael a little while ago about how he demonstrated Windows working with Kubernetes using that OVS switch extension in GC, I believe, at the Google Next conference. You might have seen an announcement from us too a few weeks ago at Container World, where we announced basically support for Kubernetes in our own Azure Container Service in Microsoft Azure Public Cloud. Behind the scenes, we've done a lot of work across the teams to make sure the networking pieces work together well based on the Kubernetes requirements and primitives. And so I'm going to detail some of those for you today. So at a high level, again, this is based on an announcement that was made a few weeks ago, and you can follow through with this example. But it creates a Kubernetes cluster using a Linux master node, and then an availability set of potentially multiple Windows cluster nodes or worker nodes. These resources and the actual Kubernetes cluster itself are formed through a resource group, which contains a lot of different objects. And so when you actually go to the Azure portal and say, I want to launch a new Azure Container Service, you're presented with some options about what type of orchestration you want to use, what type of worker nodes you want to use, and you set up some security parameters like SSH public keys, so on and so forth. Behind the scenes, that actually goes out and creates a bunch of different resources on Azure itself, like load balancers, security groups, virtual networks, public IPs, so on and so forth. What it also does, though, it uses one of the ARM templates for these Windows worker nodes with some custom-built kubeproxy and kubelet code that we've contributed to the open source community. On the slide there, you can kind of see the fork that we're working out of right now. And we're also submitting pull requests, obviously, into the master branch to get over some of the limitations that were called out earlier. And so these updates basically that go into the Azure worker node VMs for Windows for kubeproxy and kubelet allow us to overcome some of those limitations that I think you guys faced in the past, like the need to have the RAS service installed, the difficulty you had with NetSH port proxying to do TCP. I believe it didn't do UDP for you, basically, which caused problems with DNS. And so we basically made a lot of those updates in the kubeproxy code itself to do the routing, to provide port forwarding for both TCP and UDP ports, for doing DNS, pending suffixes to the DNS requests and sending them back. We've also done work on the kubelet itself to make sure we have internet access through our NAT networks. So those are some of the changes we've made to make Kubernetes work in Azure with Windows worker nodes. So let's dive a little deeper into what one of those worker nodes actually looks like from a networking stack perspective. This is kind of perhaps a complicated picture, so let me kind of break it down as much as I can. In this picture, we have 2 Windows Server containers. It could be n number of containers, though. It's not limited to just 2. But we're actually providing 2 different container endpoints, which are attached to different networks, different container networks. One of those networks is a transparent network. And so we've worked with the Azure Container Service team to basically create these networks behind the scene, a transparent and a NAT network. The transparent network itself is basically for interpod communication. And so we have multiple management host VNICs that have not only the host IP address for that container host VM, but also then a forwarder, a virtual network interface forwarder that acts as the default gateway for the pod CIDRs that are provided and allocated for this particular container host VM. On that forwarder interface in the bottom left-hand screen, you can see that there's also external IPs which are assigned to this. So if you do a kubectl apply and launch a new service, basically it'll work with the Azure load balancer to get an external IP address and then access and put that external IP address on the container host VM itself. On the other side, then that's for ingress-egress traffic, that's for interpod traffic. So we have 2 vSwitches, and this is something we're actually on our roadmap is going to be collapsing this. I can't give you any timelines, unfortunately, but we are working towards that direction because we know this is a cause for concern. The reason we've actually done this, and I have some frequently asked questions in the next slide, why do we need 2 endpoints? Basically, as I mentioned before, one's for ingress north-south traffic going through our NAT network, and then the other one is for that east-west traffic between different pods in the cluster itself. Right now, we're using a transparent network to provide that external connectivity. But again, a future solution will be combining these 2 endpoints basically into one. So it's interesting to think of through how we basically do that interpod communication. As you know, Kubernetes assigns these pod sitters basically to a host node, and then multiple IP addresses from that sitter range are assigned to the individual pods themselves. So we have to have a way to basically route between those different pod sitters. And the way we do that in Azure is using this user-defined routing table. It's actually implemented in our virtual filtering platform extension on the physical host itself. And what it does is it looks up the destination prefix of any IP traffic and then sends it to the next hop, which is actually the IP address of the container host, that cluster IP address, through its gateway. And so on the left-hand side, we see that the pod sitter range for this container host is 10.244.1, whereas the one on the right is 10.244.2. So whenever a container in the Windows container host on the left needs to talk to one of the IPs on the right, it's going to go through that vEthernet virtual network adapter forwarder interface, which is its gateway IP address, and then it's going to get sent to the physical host. The physical host then, through the VFP extension rules that implement the user-defined routing, will do a lookup and see that the next hop for that prefix, for the IP address in that prefix, needs to go to this second container host on the right-hand side. And so that's how that east-west traffic goes to share between different container hosts in Azure. I'm running out of time here. I apologize for going somewhat quickly through this, but I do have a few more slides I want to show. Basically, ingress-egress traffic flow. Again, we're using an Azure load balancer, which is publishing a public IP address. And so an external client basically can access that service through the Azure load balancer public IP address. On the back end, then, the Azure load balancer is sending these out in a round-robin fashion in conjunction with doing some health probes and monitoring to make sure these worker nodes are up. But it's going to be sending it to one of these kube proxies that's running in the Windows worker node itself. The kube proxy can intercept or see that traffic, and then depending on where the service is actually running, it's going to redirect that on the back end side and send the traffic to that service, represented by the purple circle on the bottom there. That's that ingress-egress traffic flow. So another thing we're actively working on is the CNI plugin. And in fact, there's a pre-release of this work that someone on our team did recently for both Linux and Windows for a CNI plugin, specifically for the Azure environment itself. This will actually be a change in the way, once this is fully implemented, it'll be a change in the way that we do the networking, in that we're not going to be using our transparent or NAT networking modes anymore. We're actually beginning to be connecting these container endpoints directly to Azure virtual networks themselves. And so this is a new announcement that went out, I believe, today from the Open Networking Summit about Azure VNet for containers, allowing that ability to not only attach your container endpoints to your Azure virtual network, but also reach back and attach the VMs that may be running in your Azure virtual network space also. We're using L2 tunnel networks just because we want to be able to apply fine-grained network policy for each container endpoint using that VFP extension on the physical host itself. So we're really excited about this to be able to introduce this, and looking for a lot of feedback and buy-in from the community on how we can make this better in the future. With that, I wanted to kind of switch over to just a quick demo and show you guys what all this looks like from an Azure perspective. I'm out of time. Michael, I don't know if I can keep going for a few minutes or if you want me to stop now.
I think you can keep going. Since we're recording this, if someone needs to drop off, they can always come back and view the recording. So it's fine to keep going. I already moved my meeting, so let's go.
Okay, cool. Let me need to share a different part of my screen now. All right. One more screen I need to share. I'm not seeing it on this window in Zoom. If I just bring up a window, can you guys see this Azure portal window that I've brought up?
All I see is the command window right now.
Okay, and let me try to do the entire desktop then. How about now? Is that something you can see?
Yeah, I see the portal now.
Okay. So what this portal is again, all of the Kubernetes instantiation is represented in a resource group. And that resource group is made up of a bunch of different objects itself. I'll try to zoom in and make this a little bit bigger if I can.
Do you have Zoom Meet installed? I
do, yeah. I'm just going to keep going. I'm not able to bring it up right now. Basically, you have a bunch of different types of resources. And so on the right-hand side of the screen, you see a bunch of different availability sets that we talked about, the load balancers, network interfaces, and VMs. And so all of this gets created for you when you launch an ACS Kubernetes instance. What then you're able to do is actually through the public IP that's exposed through the Azure load balancer, I can actually run commands, kubectl commands, basically on that cluster itself by accessing the Linux master node. So if I do, a simple operation like getting the different nodes that are available, I see that I have this 1K master node, which is a Linux node, and then 2 worker nodes, 58F03, so on and so forth, that are actually the Windows nodes themselves. I also then can launch services, and I believe I've already launched one service here. And so again, this is all from my local desktop, and I've just set up SSH tunneling to basically be able to connect to the Azure backend, or the Azure Linux master node rather. So I have this basic Windows web server that's running with a cluster IP address of 10.0.220, and then the external IP address that's advertised through the Azure load balancer itself. I can then take a look and see what pods consist of that service or make up that service. And right now I only have one. And so I'm going to try and go ahead and bring this up, accessing this service. Or actually, before I go there, I want to show you just the service definition in the YAML file. I'm sure you're familiar with this. This YAML file kind of describes what that service is. It describes whatever ports are needed to be accessed, specifically since this is a web server, we're running through port 80. It also then has the different container images that are going to be launched. And so the base image that's going to be launched is this Microsoft Windows Server Core image launched through Docker. And then it's going to invoke this PowerShell command basically to start things running. So that's the specification file that I actually gave to create this particular service. So if I go back to my kubectl and get what the external IP address is, I should be able to access this. And it's really a simple service. I'm hoping it comes up here. If not, I might need to move on.
Is there a port associated with the service as well that you need to enter beyond the IP address?
I don't believe so. It should be published on the external public port.
No, do a describe service.
Okay. Looks like it might still be working on creating the load balancer.
Yeah, so your port is 80.
Yeah, I'll think about that.
Yeah, if you're internally and you're hitting the 10.star IP address, then you'll be on 3460.
Right. Okay.
But externally, it looks like you're hitting the so you basically got a single IP address for this specific service from the Azure load balancer.
Yep. Yeah, that's what's being advertised externally. So if we went back to the Azure portal, you'd actually see this IP address. But just for the sake of time, I'm gonna move on. And what's happening though is it's basically redirecting those requests to the kube proxies on the different boxes, the Windows worker node boxes. So if I bring one of those up, you can see some of the stuff that I was describing before, where we basically have this virtual network adapter called the forwarder adapter and some IP addresses assigned to it. If I go ahead and just look at some of those IP addresses, you'll see that one of my old external public IP addresses is assigned to this, as well as a bunch of service IPs for the Kubernetes service itself. There's also then the transparent network that I can look at and see. Oh, excuse me. I believe it's called internal port.
It's the forwarder. Jason, it's the forwarder.
Oh, it is forwarder? Okay. Yeah, so we also have the default gateway IP address for this particular pod slitter here assigned. And then again, as I mentioned before, all the different service IPs below.
If you're looking for the transparent one, try the internal port.
Yeah, I was looking for the host IP itself. Well, that's okay.
Do IP config. IP config.
Okay.
That's the transparent one.
So this is the transparent one. So that's the virtual network adapter for the actual host IP address. And then the IP address is assigned to that virtual network adapter. Then again, these are all the different service IPs that are created by Kubernetes, including the external IP that's assigned by the load balancer itself. Let me go back to my presentation. Yeah, so we answered some of the frequently asked questions about the 2 container endpoints, some of the stuff we're doing to resolve those changes in the future. Kind of touched on DNS as well, and some of the work we did in kubeproxy to make DNS work, not only to append those DNS suffixes to requests coming in to do this full domain name resolution, but also returning the answers. And then working with the Azure load balancer and kubeproxy to basically set up that load balancing on the service network. I'm out of time, but I want to say just real quickly too, we're presenting some more, we're building some more capabilities with an overlay network driver that allow you to do this same type of thing with on-premise based deployments. You can, of course, do this today with a lot of physical network configuration, but we have an overlay network driver that we're going to show in a future demo that basically shows how you do this on-prem without needing to mess with any of the physical network configuration. Then also we're continuing efforts to make a CNI plugin that will work for on-premise deployments also. So what's next? We definitely know that there are some gaps in the solution today, but there are opportunities basically for you to kind of join us on this journey, as I mentioned at the beginning of the call. And if you're interested in getting some of those builds, please do reach out to me, and especially if you have any customers or if you're just interested in understanding the direction that we're going. There probably will be a way that we can provide some insider builds to you to help us validate some of these solutions. You'll also note that we're on an increased release cadence, and so instead of waiting multiple years for a new version of server to come out, it's not going to be that long anymore. It's going to be several months. And so not only are we going to be providing these kind of insider builds or some mechanism by which you can try out these features during our development, but you're also going to be able then to have access to those builds at a quicker release cadence as they become available. So I'd love to hear more from you guys and love to be more involved in the community. But with that, I'll turn it over, and if you have any questions for me, I'd love to be able to field those now. Since this is a recording, I'm not sure how many people are left.
This is Alin from Cloudbase.
Yes.
I have a few questions. So one of them is regarding the CNI plugin that you are developing right now. Can you share the fork or at least the direction you're going to integrate Linux and Windows together for the CNI plugin under Kubernetes?
Yeah, so we showed the Azure one a few slides ago that was based for that. The on-premise one, Dinesh, I don't know if there's any fork that we're working out of yet for that.
We will share it offline. Like we'll follow up and we'll share it.
Yep, that will be available on the GitHub repo, so we'll let you know where that is.
Okay, thank you. And another question is, you mentioned that the Azure load balancing is providing you the rules for the forwarding IPs inside the forwarding extension. Are those APIs publicly available?
The APIs for creating the different ARM templates and resources are definitely publicly available. ACS Engine itself is a public project, and so you can definitely go onto the ACS Engine GitHub repo and see kind of the commands and parameters we've done to hook up that load balancing and put all those different resources together. I don't think I have a link for that particular repo on my slides, unfortunately, but I can provide that to you offline.
It would be great, thank you.
Just one more thing to add for ACS Engine. It also allows you to create the mixed Windows and Linux clusters so that the containers and the mixed Windows Linux Kubernetes cluster can talk to each other.
With that, if there's no other questions, go ahead and say thank you. Thank you for the team also, Azure and the Windows Networking Engineering team that done a lot of this work for us in the content. And again, we'd love to be more a part of the community. And so I think you'll see us more active on the Slack group. I know Anthony and others are already there, but I think the Windows Networking team you'll see there more frequently as well. So look forward to chatting with you more. And again, if you would like some more details, we can look for ways to share those with you and even provide builds in some cases.
Awesome. Jason, thank you for the presentation. Thank you, Anthony, Dinesh, and the rest of the team. This was very informative. Obviously, we look forward to continuous engagement. We look forward to seeing the network overlay driver, some of the CNI plugins. I think that's, folks from Cloudbase, as our dean have mentioned, this is going to be an important building block for us to deliver additional solutions, whether that's Cloudbase delivering an OVN or OVS solution or other vendors coming and building on top of it to produce hybrid solutions across Windows as well as Linux. So this is a great building block, and we look forward to getting more details and getting to the point where these guys get their hands on it. So I know you have talked to Alessandro from Cloudbase in the past, so we're getting close, so we can feel it.
Yep.
All right. Thank you, everybody, for attending. We'll see you guys in a couple of weeks.
Okay. Thanks, Michael.
Thanks a lot for the presentation. Bye-bye.
Bye.